Today we take up our final topic, which is on counting. So, what is the nature of counting? What is it to count? I mean, what is it good for? Why do we do it? Well, we do it to get a sense of the size of a particular collection of things, or to compare the sizes of two different collections of things. That's probably what it was originally used to do, to compare the sizes of two different collections. So when we think about counting from that perspective, generally, we'd have two collections of things, right? And what you would think to do is, what we do is say, okay, you have 1, 2, 3, right, etc., until you get to the number 6 here, and on the other side we have 1, 2, 3, etc., right, until we get to the number 4. And so we've assigned these numbers to represent the quantity of things in each of these collections, and we know that 6 is bigger than 4, so we know that the first collection is bigger than the second collection. But what I want to argue here is that this is actually not as simple as it could be. This is actually more sophisticated than it has to be, because we're using these labels here, the 6 and the 4. The 6 and the 4 are numbers that are an additional layer of abstraction here. And so really we sort of have this third set, our set of natural counting numbers, 1, 2, 3, 4, 5, and when we're counting in this way, we're using this set as an intermediary to our calculation, or to our comparison of the size of these things, right? So we're allowing this set to sort of come in the middle of the two sets that are right in front of our nose. So say this is A and this is B. You probably know from experience, if one of these collections, say A, had a large number of things, right? It's easy to lose your count and start thinking about what you're going to have for dinner or whatever, as you're going through the elements of your set and counting off 1, 2, 3, 4, etc. So there's a much more efficient way of comparing the size of our two sets that doesn't involve the concept of number, at least not at the outset, not as a primitive notion. So what you can do is, you just have your two sets, staring you in the face. No need to get a third set of numbers involved to make the comparison. All you have to do is sort of pair elements of A off with elements of B one at a time. So you have this element here, maybe you pair it with that one there, and this, and you pair it with that one there, and this, and you pair it with that one there, and this, and you pair it with that one there. And now you're out of elements of B, but you still have elements of A left over, right? So you could confidently conclude what we would write in our notation here, that the cardinality of A is bigger than the cardinality of B, right? The size of A is bigger than the size of B, just from this simple pairing off process. What you might notice is that this pairing off process, it looks suspiciously like a function. I'll just say suspiciously function-like. So here's a question for us. So what does counting and cardinality have to do with functions? So basically there's 3 cases that we'll examine. So here are the options. So in the first case, let's look at when the cardinality of A is less than or equal to the cardinality of B. And we're talking about finite sets here. Okay, so the sets are finite until I say otherwise. So if A is smaller than B, when we do our pairing off process, so we take our first point and we pair it off with something, we take our next one, we pair it off with something, take a third, pair it off, and you go on like this until you go through all of the elements of A. Well, once you're through all the elements of A, you've put them into correspondence with a subset of B, right? So in other words, you've created an injective function from A to B, right? So in this pairing off process, you sort of have to imagine you have like two big piles of nickels or something, and you put your left index finger in one pile, the right index finger in the other pile, and you sort of move those two nickels off together into a pair, right? And so you're never, when you do that, you're never taking two nickels from the left-hand pile and assigning them to one nickel in the right-hand pile, right? Because you're pairing nickels off together and sort of making a third pile. So you're never going to have a function that's not injective that way. So anyway, in this case, we see intuitively that there exists an injective function that takes A to B, right? And conversely, if there is an injective function from A to B, that establishes a correspondence between the elements of A and a subset of B, which is just the image of A under F, the range of F. And so that means that the cardinality of B has to be bigger than or equal to the cardinality of A. So in fact, this is an equivalence here. If, on the other hand, the cardinality of A is greater than or equal to the cardinality of B, then when you do your pairing off, right, you're going to run out of things in B before you run out of things in A. Right, so there's going to be leftover stuff in A. And if you wanted to pair those leftover things with things in B, then since things in B already got hit, right, that's going to necessarily assign two different things from A to the same output, right? So what you would have is you would have a function which hits everything in B, but might have to hit things in B more than once. So it might not be injective, but it will be surjective. So there exists a surjective function from A to B. And if there exists a surjective function from A to B, well, everything in B gets hit. So sort of reversing the arrow, that means that there had to be at least as many things in A to do the hitting. Right? So this also goes both ways. And then combining these two is the third case. If your sets have the same size, then when you're doing the pairing off, they're both going to be exhausted at the exact same time, right? So in that case, everybody in A pairs up with exactly one thing in B, and vice versa. Everything in B is paired up exactly with one thing in A, and so there would exist a bijective function from A to B. So I hope what I've provoked you to think about is the concept that perhaps functions and functions between sets is a sort of more primitive notion even than the notion of number and of counting. In some sense, we should be able to build up just the whole idea of the cardinality of a set, the size of a set, or the relative sizes of sets, just by using the language of injective, surjective functions between sets. There are surprisingly strong consequences just from these simple considerations. So the main consequence is encapsulated in what's called the Pigeonhole Principle. And you get the Pigeonhole Principle by taking 1 and 2 and phrasing them in terms of the not. So for 1, we would have the not of the left-hand side implies and is equivalent to the not of the right-hand side. So in particular, if the cardinality of A is bigger than the cardinality of B, then there does not exist an injective function from A to B. And for the second one, if the cardinality of A is less than the cardinality of B, then every function from A to B fails to be surjective. And the reason this is called the pigeonhole principle, that mostly comes from the first half with the not injective part. What you imagine is, so the intuition for it is that you have some holes where pigeons go to sleep, and so these pigeonholes, there's 4 of them, and you can let's say there's 4 of them, and you can imagine 5 pigeons, right? So this is your set A here, and this is your set B. If you have 5 pigeons trying to find their way into 4 holes, then it definitely has to be the case that one of the holes has at least 2 pigeons in it, right? So best case scenario, they each go sort of for the first one they see. They try to avoid each other, but inevitably there's going to be like at least that clash over that hole there. And it could be, so it doesn't have to be like that. Like there could be a hole with 3 pigeons in it, right? So maybe all 3 of these guys converge on that one, and then you have something like that. But it definitely can't be the case that they all get their own hole, right? So that's intuitive enough. And then the other part would be, I guess, if you had 4 pigeons going for 5 pigeonholes, then what you know is that at least one of the holes is going to be empty, right? So it could be the case. I mean, it could even be the case that in this case, 2 pigeons go into the same hole, but what you're definitely assured of is that one of the holes is going to be empty. Okay, so that's what the pigeonhole principle says, and it's surprisingly, shockingly powerful thing, even though it seems so simple. So to illustrate the non-intuitive power that's inherent in the very intuitive pigeonhole principle, let's take a look at the following theorem. So the theorem says that if you take a subset of the natural numbers from 1 to 100, and that subset has 10 elements in it, right? So you just pick 10 numbers between 1 and 100. Then of those 10 numbers, you can find 2 different subsets of those 10 numbers, right? So you randomly pick 10 numbers, and then within those 10 numbers, you can find 2 different subsets there, and they don't have to be of the same size, but for which the sum of the elements in each of those different subsets of your subset of 10 numbers, the sum of those elements are going to be equal. And so you add up, so you can find 2 different subsets in this set of 10 numbers where when you add up all of the numbers in them, you get the same sum. So to see how kind of weird this is, you can consider the set A here, which has 10 elements, I think, as you can verify. And you might see, I mean, it's not so obvious that there should be 2 subsets here that add up to be the same thing. It's like one easy thing you could try is to take, say, one of your subsets to just have, say, the number 50 in it. And then it just so happens that 50 is 18 plus 12, that's 30. And then 11 is 41, and then 4 and 5 make 9. That's going to add up to 50. So those will have the same sum. So we got kind of lucky there, but our theorem is supposed to apply to any 10-element subset. So if I change this 4 here to a 3, then that's not going to work anymore because those. Now that so I'm going to decrease the sum from that subset Y I had before. That's no longer going to equal 50, but there is supposed to be. I should be able to to re-choose my subsets X and Y such that the proposition still holds. So for example, I could now take X to be 80 and Y I could make that 50 and 12 and 18. Right, that would add up. But if I changed, say 18 to 20, then that would no longer work. But then something like the sets chosen would work. X and Y shown there both add up to 70. So why does this always work? Well, it works because of the pigeonhole principle. And so what we're trying to do, we're looking for X and Y in the power set of our set A. And what we want is for X and Y, for the sum of those elements in X and Y to be equal. Right? So if we, let's say f of X is going to be just the sum of elements of X, right? What we want to say is that with these X and Y, which aren't equal, that they both have the same value under this function f. Right? F of X equals f of Y. Well, these are your pigeons, right? And these are the holes. The holes are labeled by the values of the function on the subsets X and Y. And how many pigeons are there? Well, that's just the number of subsets of A, right? And A has cardinality 10, so this is 2 to the 10th, which is 1024. And the number of holes here, well, we just have to say what possible range could the values of this function take on, right? And well, so the elements of X, their numbers from 1 to 100, right? But X is a subset of a set of cardinality 10, so X has less than 10 elements, right? So cardinality of X is less than or equal to 10, and the elements of X are between, so if X is in X, then X is between 1 and 100, right? So f of X then has got to be between, at worst, it's going to be 1,000, right? And in the upper range, and the lower range, well, the worst is that there's no X in X at all, right? That we have the empty set, and so the value of the function would be 0. There's nothing to add up. And so there's only 1,001 holes here. Right? So that means that you have 1,024 pigeons flying into 1,001 holes. So there's always going to be 2 pigeons flying into the same hole. Right? There's always going to be 2 subsets which have the same value by this function. So let's write that up. So we'll define f taking the power set of A to let's just say the integers to begin with, by f of X equals the sum. So the sum of X where X is in the set capital X, right? So you take the sum over the elements of the set capital X. That's the function. So we note that 0 is less than or equal to the value of f of X, and since that's the sum over the X in X, each of those X is less than or equal to 100, right? So that's less than the sum over the elements in X of 100, but there's less than or equal to 10 elements in that set capital X. So this is less than or equal to 10 times 100, and that's equal to 1,000. Okay, so in fact, we can consider f to be a function from the power set of A to the set from 0 to 1,000. Then since the cardinality of the power set of A equals 2 to the cardinality of A, which is 2 to the 10th, which is 1,024, and the cardinality of the set from 0 to 1,000 is 1,001, I guess I'll say that, and the fact that 1,024 is bigger than 1,001 by the pigeonhole principle, By the pigeonhole principle, F is not injective. Thus, there are different x, y in the power set of A such that f of x equals f of y. And that is the conclusion. So we got the pigeonhole principle by basically using these two facts here. That differences in cardinality sort of correspond to injective and surjective functions. But now I want to move into looking at the third thing here. We're going to use this in quite a different way. So for finite sets here, what this tells us is that our sets have the same cardinality, the same number of elements, if and only if there's a bijective function from one of those sets to the other. And what we're going to do with this is we're going to turn this into a definition of the size of a set for arbitrary sets. So we know what it means even for infinite sets A and B, right? We can talk about a bijective function from A to B. And in that case, we're going to use that bijective function as telling us, we're going to interpret that as telling us that the sets A and B have the same size. So here's what that definition looks like. Two sets, A and B, not necessarily finite, have the same cardinality, which we write as like norm A equals norm B, or absolute value A equals absolute value B. And just read that as A and B have the same cardinality if there exists a bijective function from A to B. And if no such bijective function exists, then A and B have unequal cardinality, and we write that as absolute value of A not equal to the absolute value of B, and just read that as A and B have unequal cardinality. So again, intuitively, what this means is the same thing as in the finite case. It's just that we can pair off elements of A and elements of B, such that every element in A is assigned to a unique element in B, and every element in B has an element of A being assigned to it. So everything in A corresponds to something in B, and everything in B corresponds to something in A. Okay. And just another little piece of terminology. A bijective function will be called a bijection, an injective function will be called an injection, and a surjective function will be called a surjection. So the really interesting stuff happens with this definition when A and B are both infinite sets. Right. So we know when we have finite sets what the same cardinality means. They just have the same number of elements, right? So the sets 1, 2, 3, and 100, 103, and 106, they have the same cardinality, right? They both have 3 elements. So not that much to say there. But with infinite sets, it becomes very interesting. So, for example, you have the set of integers, and so let's say you have 0, 1, 2, 3, negative 1, negative 2, negative 3, dot, 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 right? So the natural numbers are here, right? And the whole thing, that's the integers, and the natural numbers is a strict subset of Z, right? So you might think that from this, in some sense, the natural numbers have a smaller size than the integers. But in the sense of cardinality, that's not true. The cardinality of the natural numbers is exactly the same as the cardinality of the integers because there's a bijection from the natural numbers to the integers. We can pair off the natural numbers and the integers together. And it's a very natural thing to do. So you have natural numbers, you have the integers, natural numbers 1, 2, 3, 4, 5, 6, etc. The integers, you just have to sort of write them down so that you have to write down sort of a list of all of the integers so that they correspond to the natural numbers. And what you can do is just start with 0 and then just bounce from the positive numbers to the negative numbers. So 1, -1, 2, -2, 3, -3, etc. Right, so with this pattern continuing, clearly this is going to be a bijection of the natural numbers with the integers. And in fact, you can write down a formula. So you can notice on the evens here, right? It's just all you're doing is halving, and for the odd natural numbers, I think what you're doing is subtracting 1 first, halving, and then negating. Right, so subtract 1 from 3, you get 2, halve, you get 1, and then negate, you get -1. Subtract 1 from 5, you get 4, halve, you get 2, negate, you get -2. So I think what you can do is you can define a function from the natural numbers to the integers by f of n is equal to, what did I say? So it's n over 2 if n is even, and it's n minus 1 over 2, and then the negative of that, so negative that, if n is odd. And then it would be a routine exercise, so check. So you want to check that f is a bijection. And so you could check that from the formula, check that it's an injection and a surjection. And it's clear from the list we wrote down above. But this, to be perfectly rigorous about it, this gives you, lets you see exactly that it's defined for all natural numbers. And then that'll give you a good way of checking through the formalism. So before now, you might have been tempted to say that the natural numbers were something like half as large as the integers, but this should give you pause. Really, you should think, that they're the same size in some sense, and the appropriate sense is in the sense of this definition here. Right? They can be paired off 2 by 2 using this function f that we wrote down here. Right? So there's for everything in n, there's exactly one thing in z paired up with it, and everything in z, there's exactly one thing in n paired up with it, and nothing missing on either side. So they must, in some intuitive sense, have the same size. And maybe even more surprising example of this phenomena is that the cardinality of the interval from 0 to 1 in the real numbers, that's equal to the cardinality of the interval from 0 to infinity. And so generally, you would think of sort of the size of this interval as being 1, right? The length of the interval is 1, and the length of this interval is infinite, right? So this second interval is much bigger than the first interval, but that's only bigger in the sense of distance, right? And measuring distance, but this is measuring something different. It's measuring the ability to pair off points, and in that sense, these are exactly the same size as sets. So the notion of cardinality is more primitive, right? We don't have to know anything about the distance as it's defined on R to talk about the cardinality. It's a more primitive and different concept than distance. So this is an even more sort of extreme kind of example, right? So like the natural numbers, we are tempted to think maybe it's half the size of the integers if we don't think too hard about it, and we had our intuition shattered a little bit there. This we're tempted to think that this is like, it's not even a measurable fraction of the size of the interval from 0 to infinity. Right, so the fraction would sort of be like 0. You sort of have like size 1 here over infinity. But in fact, in terms of cardinality, they're exactly the same. So all we need to see this is to construct a suitable function, and you can think about it in terms of graphs to kind of get an idea of what the function might be. So you have your interval from 0 to 1 here, and you want your function to take that interval from 0, 1 to the interval from 0 to infinity. So your input axis, that's x, that's with your interval 0 to 1. Your output is y, and you want that to cover the interval from 0 to infinity. Right? So you sort of have infinity all the way up here. So what you want to do is you want some graph that sort of connects 0 over here, and as you approach 1, you have some kind of asymptote. So as you approach 1, it's going all the way to infinity. So you can start with something basic like 1 over 1 minus x, right? That has an asymptote at x equals 1, and but it's not equal to 0 at 0. Right? So what you can do is remedy that by, say, multiplying by x. So let's consider x over 1 minus x. Maybe that could be our f of x. And it's helpful to write this in an alternate form. So if we, on the numerator, it's a little trick here. We write x minus 1 plus 1 on the numerator over 1 minus x. And the point is that x minus 1 is the negative of 1 minus x. So we can write this as this is negative 1 plus 1 over 1 minus x. So it's easy to see from this that, for example, f is injective. So f is injective because if f of x1 equals f of x2, right, we want to show that x1 equals x2. Well, you have negative 1 plus 1 over 1 minus x1 equals negative 1 plus 1 over 1 minus x2. And you cancel the negative 1's on both sides, and then you invert. So you have 1 over 1 minus x1, you just invert that side, 1 over 1 minus x2, invert that side, and then again you cancel the 1's and the negatives, and you get that x1 equals x2. So that's easy. And f is surjective. And so we want to say that, so if y is some element of 0 to infinity, right, what we want to do is you want to solve negative 1 plus 1 over 1 minus x, 1 minus x equals y, right? So all we have to do is just play around with this, just put the negative 1 on the other side and then invert, and what we get is that 1 minus x equals 1 over y plus 1, and so x is equal to 1 minus 1 over y plus 1. And this is going to be a real number because y is not negative 1, so that's a perfectly good candidate. So choose or define x to be 1 minus 1 over y plus 1, and then all you have to do is do the same calculation we just did in reverse and verify that f takes that x to the given y. Okay, so that shows, so thus f is a bijection. And one thing I just realized I wasn't super clear about is that f of x actually does take values in 0 to infinity. So I should have said that f of x really is in 0 to infinity here, and that's because so x is between 0 and 1. So negative x then is between negative 1 and 0, and then so adding 1 to that, 1 minus x is between 0 and 1, and so that means that 1 over 1 minus x, that is between 1 over 1 minus x is between infinity and 1, and then when you multiply x between 0 and 1 with 1 over 1 minus x between 1 and infinity, you're going to get something between 0 and infinity. Okay, so there we have our defined bijection between 0, 1 and 0, infinity, and so those two intervals have the same cardinality. And the book does a cool thing. It derives geometrically. It shows you that this bijection is the same one you would get from considering the interval from 0 to 1 like this, and the interval from 0 to infinity along the x-axis. And it's what you would get if you had your eye at the point -1, 1, and were to look through the point. So here's your x. If you were to follow your line of sight to the axis down here to this point, that would be your output point y. And so here this y is the same as, it's not hard to just using slopes to find out that this is the same as x over 1 minus x. So it's a geometrically motivated way to think about that. It's sort of projecting your line of sight from a screen here onto the ground. Okay, so that's an introduction to cardinality, especially for infinite sets. And next time we will discuss the fact that there are really different sizes of infinity, so that there are different sets. So two different sets, A and B, that are both infinite, but that are not in bijective correspondence. Right, so in particular, we'll show that the natural numbers, that there's no function which is surjective from the natural numbers to R. And so we have a function from n to r, f is not surjective. Right, so in particular, such a function can't be bijective. So this in some sense tells you that the infinity of the real numbers is larger than the infinity that's represented by the natural numbers. All right, that's all for now.